So we've navigated.
All right.
Professor. I think she's a new just became a professor.
Yeah. 52 average. And I'm pretty sure it's only a 52 because someone got a 96. So it would have been like a 30 otherwise. I think like only 4 people got more than a 70. The rest of the class got like below 60.
It's going to be a fun distribution.
Yeah, it's not a good. It was not a fun distribution at all.
Yeah.
No curve. No curve. She's just giving us a chance to get 10% back. Well, 10 points, but like it's out of 100, so you're getting 10.
So if everybody in class does
All right. Sounds like y'all have been having a fun afternoon.
I've been having a fun month,
Uh-oh.
but I have another fun 2 weeks.
All right. So, let's see here. We've got another lab to do today. So today we're going to be doing a 3D frame, but with area loads. And that's not displaying yet. Sorry, there we go. That's better. Now you can see what I'm doing.
Inventor. Is there a computer lab with inventor?
Probably. Look it up on OTS's site. They've got a web page that tells you what software is where. Let's see here. Okay, so why would we want to do a 3D frame with area loads? Well, most of the time we're not usually using point loads or just straight up distributed loads when we're analyzing buildings. A lot of the time, the loads we're given are in area loads. So we have a pressure basically. So this is pretty obvious when we have like wind pressure blowing on the facade of a building or something like that. But it's also useful for estimating interior loads too. So it's a lot of work trying to be like, oh, we're going to have all these partition walls here, here, and here. So these are where all the loads are going to go in a building. And, you know, that stuff can change throughout the life of the building. So usually what we do is we have a fairly conservative kind of area load we design for throughout the building. So in a lot of residential construction, we usually design for 30 to 50 pounds per square foot of dead load and live load. And in commercial, that can go up to about 100 pounds per square foot that they usually design for in live loads. And this depends based off of the type of building you're trying to design, basically. These loads will come from your building code or like ASC 7 or some other documents like that. And you'll get to come to enjoy all of these in the coming years if you're in structural engineering or taking some of those classes. So let's show you how we go and put a frame together and add some area loads to it. So today we're going to do a 3D frame that's in figure 1 here. It's going to consist of 3 bays in the X direction, 2 bays in the Y direction, and 3 stories. So it's going to look like the 3D frame we did 2 weeks ago. I believe it's the same dimensions and all, so similar to that. Beams will be similar here. W16 by 77, W18 by 97, making it out of steel. Units we're using today are pounds and feet, so that's different. Why are we using pounds? We're doing that because it's real hard to define area loads in kips per square foot, because we usually do not have loads that big. If you need 1,000 pounds per square foot somewhere, that's a very specialty type of structure you're using. It's usually in the tens to hundreds. We'll have our same 2 load combinations, dead load, live load, and wind load, and some deliverables here. So while we get SAP up and running, are there any questions on the lab for the class? Everyone good with all this so far?
I'm never gonna be able to use SAP for the homeworks.
That's a good question. Well, nothing's stopping you from checking your homeworks with SAP. It's actually a very good check on what you're doing, but it's also good that you're able to do it by hand too, because that's what I would say. You don't always have SAP in your pocket, but VCL helps with that a little bit more now. It's useful to be able to go and calculate those things real quick if you need to. And it's good to know what it should be just to make sure you plug the right thing into SAP, basically. So practicing one, practicing the other. After this class, you can pretty much just double check stuff with SAP at that point. Well, there's a good number. Usually companies will specialize in one or two programs, depending on the scope of what the company's doing. Some are better suited for certain applications than others. SAP, for instance, is a really good general purpose analysis engine. So that's good at doing the structural analysis. A lot of times, and you can also do like design work with SAP too, but that's not quite as built in into this version here. You'll have other versions like eTabs or there's a lot more. eTabs is a big one I'm thinking of that they use a lot for concrete buildings. There's like RISA and RAM. Those are all also really good analysis and design products. There's a lot of these, and usually you'll have like one or two at your company, basically. But if you know what you're doing in SAP, you're basically doing the same thing in any other one of those. It's just, figuring out where they want to change the options to, basically. Yeah, so I mean, you're basically doing the same operations here. It's just going to be, a little different based off of how they implemented it in the different softwares. Yeah, so it's like programming. Learn one, you can learn the rest of them pretty easily. This is getting you 80% there for the rest of them too. And it's the procedure of how you want to learn the analysis for doing a type of structure, basically. And then you'll know how to just actually doing it's just which buttons you press in the other program to do the same thing, basically. Okay. Any other questions? Cool. So let's get started. We'll make ourselves a new model. And we're going to be following the same steps we followed 2 weeks ago to start initially setting this stuff up. All right, so first things first, we're going to make sure we're in pounds and feet for our units this week, because that's the units our lab is suggesting we use. So we'll do that. So pounds and feet here. And then we're going to do our grid only template, or sorry, no, we're not going to do grid only. We're going to do a 3D frame. And there's two ways we can do this. We can go and do it the way with the open frame building here, which is what we did last week. And I'm going to show you that today because I think that's a good procedure. What we can also do is we can do a beam slab building here, where we go and do a bit of modification to the slab here. We don't have a slab in this model, but effectively we're going to be putting in a kind of zero width slab on there to go and catch the area load and distribute it to our frames. So I'll show you how we do that, but we're going to use an open frame building in our template today. If you remember from a couple weeks ago, our dimensions aren't even here. So we need to use the custom grid spacing. So we'll click on that, click edit grid. And here we'll put in the ordinates for all of the different axes of our building here. So for our x-axis, we'll be at 0, 15, 27, and 42. For our y-axis here, we'll be at 0, 10, and 20. And then for our z-axis, we'll be at 0, 15, 27, and 37. Okay, any questions on that? So everyone got their ordinates 0, 15, 27, 42, 0, 10, 20, and 0, 15, 27, and 37. All right, so when we're happy with that, we can press OK. That gives us the grid spacing we want. Let's turn off restraints because we want these to be fixed. And then let's go and import the two sections we want to use. We're going to be doing a W16 by 77 and a W18 by 97. So we'll import those new properties. They're wide flanges. Click on AASC15, open that up, scroll down to W16 by 77. We also hit Control. We can pick up 18 by 97 while we're in here as well. And we can press OK when we got both of those. And then OK again, and then OK again. And now we have both of these imported. Our beams will be the 16s, and then our columns will be the W18s. Okay, any questions on that? Anyone need another second? Okay, so all of these options are good, so we'll press OK, and it'll generate our template here. Let me close our plan here. First things first, let's go and put it in. Let's go and put on our boundary conditions. We want those to be fixed. I'm going to switch my perspective here so I can line it up a little easier. I'm going to select those 12 points at the bottom. Then we will go to Assign, Joint, Restraints. We'll select our fixed restraint here, press OK. And now we've got our 12 fixed restraints at the bottom there. Okay, any questions on that? Cool. Okay, so that is all the geometry we need to do. In our model here, we have three types of loads: dead load, live load, wind load, same as we've been doing. And we want to put together two load combinations. So let's go and do that now. So we'll go to Define, Load Patterns. Dead load's already defined. We want to keep the self-weight, so we're good there. Let's go and make ourselves a live load. Add that. Then we'll make ourselves a wind load. Set that to none and add that. So same loads we've been doing. Everyone okay with our load patterns? Okay, so we'll press OK there. Now let's go and define our load combinations. So we'll go to Define, then Load Combinations. We'll add a new combo. So our first combo is 1.2 times the dead load. So we'll add that to our list here. And be 1.6 times our live load. So we'll add that. And then it'll be 0.5 times our wind load. So we'll add that. So we'll have 1.2 dead load, 1.6 live load, and 0.5 wind load. When we're happy with that combination, we say OK. Then we'll add another one, load combination 2. It's going to be 0.9 dead load, and then 1.0 wind load. We'll add that, and then we say OK. And now we've got our two load combinations. Okay, any questions on that? All right, so I'll say okay there. And now we can get to the new stuff for adding um, our load here. So first thing we want to do is we want to go up to define here. And then we'll go to section properties. And then we're going to go to area sections. So define, section properties, area sections. Now here, what we want to do is we want to say add new section. Yeah, shell's fine. So we'll say add new section. And what we're going to do here is we'll give it a name. So we're going to call this, I don't know, whatever you want to call it. You can leave it as asec1. I'll just call it, I'm not thinking of a good name. So there we go. So I'll call that a 0 width plate. Now over here, the thing we want to change here is the thickness. So right now it's 1 foot thick. So we see our units are in feet. So it's saying we have membrane and bending thicknesses of 1 foot. We want to change these to 0. What's that? Okay, sure. So we'll set both of these to 0. And then we'll say okay. Now, yeah. It's a type. So there's a couple different types of these flat types of elements that the computer can handle. There's shells, planes, and asolids. These just depend on which directions you plan on loading it in and what characteristics you want it to keep track of. Like asolids, the most robust, shells kind of a good medium, and planes the least robust there. Though the more robust it is, the more computation time it takes. So there's trade-offs there. We don't really need to take advantage of any of that stuff today, so we're just going to leave the shell. Okay, any questions? So if you noticed when we were doing that, this is made out of 4,000 PSI concrete here. So the reason we set it to 0 thickness is so that concrete's mass doesn't contribute to our structure and add forces there that we don't want. All we want to be doing with this one is for it to distribute the area load to our beams. Make sense? Okay. So when we're happy with that, we'll say okay. Okay, so the next thing we want to do now is we want to draw in our areas. So we do that we can do that with these tools here. I'm going to use the draw poly area here. So we'll click on that one. It's the square with the corner kind of nibbed off. And you see here, we have a couple options here. There's basically how you want to draw it. That's fine. And then there's a section. So if you see, there's the 0 width plate. That's the one we had just done. So we'll make sure we select that. Now, what we're going to do is we're going to draw basically a plate across each of our floors. So we're going to do 3 of these plates. So we're going to, what we need to do for this tool is we need to click each of the corners of the floor. So I'm going to click this one. I'll click this one. And you see it's kind of starting to drag from both of those now. So we're basically drawing an area with this. I'll click the 4th one, and then I'll press right click. No, that didn't do it. So you click all 4, and then you press enter. Now, if you're Now, this might be helpful if you put it in the kind of ISO perspective view here. If you're having trouble picking out which point in the kind of orthographic perspectives there. So we do that for the first floor, or I guess first, second, and third floors here. We go and click all 4 corners and then press enter. So when we're done, we should have basically 3 red rectangles on our model like that. Does that make sense? And when we click on it and right click, we can see that it has a 0 width plate section for that. Okay, any questions on that so far? Okay, so next we need to apply our loads. So first thing is we want to apply our dead load and live load. And these are going to be area loads, and we're going to apply each of these to our 3 plates that we just did. So first, we're going to do a 30 PSF dead load. So let's go and click on our 3 plates to have those selected. And we'll see we have 3 areas and 12 edges selected in the bottom left here. We've got our 3 areas selected. So we're going to go to assign. And now we'll go down a couple more than usual and click on area loads. And then we're going to say uniform to frame. So that's going to be the 3rd option there under area loads. And what that does is it takes the area, it takes the area load that goes onto that shell there, and it distributes it to those frames that it intersects with. So click on uniform to frame there. The type of load we want is a dead load, so we keep that. We have our coordinate system here, that's global, that's fine. The load direction is gravity, that's fine, we want it going downwards. And then the load distribution. There are 2 options here, 1-way and 2-way. 1-way is it basically says this plate that we drew here is going to act basically like a really wide beam, and it's going to bend like a U between 2 sides. And 2-way describes bending action where it does that in both ways. So instead of just like a 1-dimensional kind of extruded U, it goes and does that in both ways. So it kind of sags in the middle, but it distributes it to both ends of the plate, basically. Does that make sense? No? So 1-way, it's simpler. It's kind of like bending that we've been doing in class. 2-way, it's like doing bending, but in 2 orthogonal directions. It's bending between these 2 sides and then bending between those 2 sides. And yeah, exactly. So it's like a bowl between the perimeter beams there. And 2-way is a little more computationally advanced, so we don't really teach that one, you guys, how to do that by hand, but the computer can handle it. So we can design for that using the computer. We usually get better structural performance if we design it to do 2-way bending. So, you know, less deflections, stuff like that. And we can usually make it a little thinner too. So we'll click on 2-way here. And then our uniform load here. This is where we want to put in the 30 pounds per square foot. And then we can say, okay. So we've got dead, 2-way, 30, and then okay. And as you see here, instead of putting on a million arrows, it's just gone and given us a number here. So we've got X, Y, and Z forces on this area here, or pressures components. So 0 in the X, 0 in the Y, that's fine, nothing horizontal here. And then minus 30.0 in the Z there for all 3 of that. Make sense? Now we're going to do the same thing for live loads, except for 100 PSF. So if we press Control J, we can select those 3 plates again. Then we'll go to assign. area loads, uniform to frame. And then instead of dead, we'll have live load. It's still going to stay two-way. Instead of 30, we'll put in 100. And then we can say OK. And now we've got our live loads here, and we see it's 100 pounds per square foot. Okay, any questions on that? So that's the big new thing we're doing this week. So in structural analysis, there's different types of elements, basically. So far, we've been using these one-dimensional elements, these frames and trusses, basically. So those are all 1D. They're basically much longer than they are wide or tall. We've now got some 2D elements we're using, so these plates. In this case, we're just using it to collect an area load and distribute it to the rest of the 1D elements we've modeled here. But we do use these plates in structures as well. We use them as floors, we use them as walls, stuff like that. And in the next couple labs, we'll cover, or in the next lab, I'll cover like a structural use for plates as well and how we can analyze that with SAP. And that's starting to go beyond kind of the scope of what we'll be doing by hand calculations in this class. Okay, so we've done that. And then our last thing we need to do is our wind loads here. So the 10, 20, and 30 kips. So we're just going to add those on our windward face of the building here. So we'll select our 3 nodes here, and we'll just add them as point loads like our direction said we should. So we'll go to assign, joint loads, forces, change that to a wind load. And if you remember, this is going to be in 10 kips going this way, but our units here are in pounds. So we can either change our units to kips here, or we can just put in 10,000 pounds. So I'll keep it in pounds and feet here, and we'll want to put in 10,000 there. So either way works. So this one will be 20,000 pounds. And then the last one will be 30,000. Okay, any questions? Okay, cool. So that's all of our loads. We're ready to analyze our model now. So let's run it. Gonna turn off modal here. Run it. It'll want us to save it. So let's make ourselves a new folder. And run it. And then we will get our deformed shape. Okay, so let's look at the deliverables we want to do. Everyone able to run it and get in something close to that? Okay, cool. So let's see here. We want to look at the reactions for each support with the values and arrows for the XZ frame at y equals 10, subject to load combination. Okay, so y equals 10 is the frame in the middle there. And if we've done all our analysis right, these should be larger reactions than these 2 outer frames. Why would that happen in this case? Well, we've got area loads and we're doing 2-way bending. So let's see here. It's going to distribute it to both these sides as well as both these sides. So unlike last week where we were only, or 2 weeks ago, where we were only having forces on just these XZ beams here, we now have forces on all of them. So these kind of middle columns here are getting forces in 2 directions now, instead of just the one direction of these kind of y equals 0 and y equals 20 column lines here. So we're going to expect these reactions to be big. So let's go to view, set 2D view, go and click on our XZ plane here. let's put in 10 feet. And then apply there. Then let's go to joints. What did that say? Load combination 1. And then we can say okay. Okay, any questions on this? So we've got our reactions here in pounds. So we've got about 86 kips and 93 kips on these two middle ones here. This is the one it would be looking for here, but let's just say we want to look at the one at y equals 0 here. This one is now only 45 kips, and this one I can't quite read. It looks like it's about 52 there. Okay. So we see that these loads are smaller than the other ones. So it need to make sure we're clicking the right plane here because they are different in most applications. Okay, any questions on that? So next, let's look at the deformed shape for the XZ frame at y equals 10, subject to load combination 2. So let's set our view to y equals 10. And then let's look at our deformed shape for load combination 2. Set the wire shadow there. Press OK. And we get our deformed shape looking like that. All right, so that's the deformed shape. Any questions on that? Okay, then the story drift values for the right bay of the XZ frame at y equals 20, subject to load combination 1 and 2, and then the ratio. So let's set our view to y equals 20. And then we can look at our drift values here. So these will be 0.0235, 0.0432, and 0.0527 feet. So we're looking at those U1 values. That's for combination 2 there. We'll also want to look at it for combination 1. So we'll display this for combination 1. And then we got 0.0118, 0.0216, and then 0.0263. So we can then take the ratios of those. Those will be between like 1.5 and 2, basically. So for the report, just the 9 values as we've been doing. The drift value, 1 for each floor for combination 1, 1 for each floor for combination 2, and then the ratios. So a ratio for each floor. Make sense? Okay. Then we want to do the shear diagram and then the moment diagram for the frame at y equals 0, subject to load combination 2. And then we want to look at the max shear and moments in the second story columns. So let's go and look at our frames, cables, tendons, load combination 2, shear 2, show values. Say OK there. Let's set our view. So we want to view. It's for y equals 0. So we'll switch that there. Apply that. Should be the same as y equals 20 in this case, but we want to make sure we're looking at the right view here. And then we can shrink toggle that. So here's all of our shear diagrams. We can see that the largest shear in these second story columns here is going to be the 16,185 here in this column. So we'll note that. So that's in pounds. So same as we've been doing. Any questions on the shear diagrams here?
We started with this in pounds feet. good, it's customary to report the numbers and how.
Either work. I mean, KIPS is just, knocking 3 decimal places off of what you're getting in pounds. We did our units in pounds this time to help us with our area loads. It's gonna be, I guess, whatever standard your company usually likes to do or what your client's looking for, but this is what it is in pounds. If we want to look at it in KIPS, we can change that down here. And that'll give you those numbers instead, if you want those on your figure. Just be careful to, note what units you're using, basically. Okay, and then we do moment. So let's go and look at frames, cables, tendons. We'll switch shear 2.2 to moment 3.3 and press OK. And we've got our moment diagrams here, a little messy. And we're going to look for the largest value here. I believe that's going to be this one, but let's just double check. So this one's got a max moment of -65. This one's got a largest max moment of -104. I think this one's going to be -103. Yep. And then this one will be -68. Okay. So our largest moment here is going to be in that same column with a maximum moment of -104,227 pound-feet. So we'd go and note that. Okay, so that's all the deliverables for this lab here. Very similar to lab 5. We're just adding area loads and basically dealing with that for this one instead. Any questions on this lab? Hopefully pretty straightforward. All right then. So thanks for coming to lab today. And let me know if you have any questions.